Hello and welcome to the latest version of the Design Patterns course for embedded C programmers. My name is Martin Schroeder at SwedishEmbedded.com and I'm going to be your instructor for the duration of this course. I'm an embedded C engineer. I work with embedded RTOS. I work with firmware development. I've also worked a lot with OpenWRT development, and my specialty is programming of embedded systems. So why would you need a course on design patterns? And why do you need to learn design patterns in the first place? Well, first of all, we use design patterns to write clean and maintainable code. Design patterns are kind of like patterns of structure of the code, and they are completely language agnostic. It doesn't matter which language you use, design patterns are still valid. They enhance code reuse because you can have standardized components that follow the same conventions, that behave in similar ways. And you're being also proactive about bug prevention, because the primary reason why code deteriorates in quality and that you run into situations where you get bugs that you cannot really explain is that dependencies get out of control. And many design patterns actually help you keep dependencies under control. Design patterns are designed to separate dependencies, to separate code, to separate concerns, so you get complete separation of concerns. And design patterns are also designed to create clean interfaces to modules in your software architecture. So we use design patterns kind of as a way to organize the little details that we express in the code, but at a higher level. So we get a clean organization of the whole software architecture. And design patterns are also essential for effective DevOps, because design patterns provide you with expectations. You can place expectations on your code, and if you follow the design patterns throughout your project, for example, as a simple example, we could take the return value pattern. If you follow that pattern throughout your project, it becomes very clear what each function returns as a status code. So when you look at code that actually checks return values, it becomes very clear what the code does and why it responds in a certain way to a certain type of value. For example, less than 0 means error, then you do error handling. If you don't use design patterns, you cannot place those expectations. You need to dig through the code and find all the details, and it takes longer time to review code and review merge requests. So design patterns directly improve your effectiveness of your DevOps process. In this course, we're going to look at 4 main categories of design patterns. So we're going to look at creational patterns. Those patterns focus on standardized way of creating new objects and handling memory ownership. We're going to look at structural patterns. Those patterns deal with structure of our code and allow for easy extension without refactoring. And we're going to look at behavioral patterns. Those patterns concerned with behavior and ensuring consistent behavior in different situations. We're going to also look at concurrency patterns, and these patterns are concerned with thread synchronization and concurrency. We have 3 main types of concurrency in embedded systems. We have multiple CPUs, we have concurrency between interrupts and threads, and then we have concurrency between threads. So we're going to look at different patterns for handling exclusive access and data sharing between all of those types of concurrency. So in the creational patterns, we're going to start with the object pattern, which is the most important pattern in all of C programming. When we start applying the object pattern, where we operate on objects and we pass a self pointer to our functions, we can organize our code in a much cleaner way. So every other higher level pattern is based on the object pattern, and we use the object pattern as the basic way of organizing our code into independent modules. We're then going to look at the opaque pattern, which allows us to hide the actual data definition of our object. We're then going to go to singleton pattern, which provides a way of enforcing just a single instance of that particular object throughout the application. It's a very simple pattern. We'll look at the factory pattern, which is a pattern where we create objects based on a data definition of the object. So device tree is a good example of the factory pattern. And we can use the factory pattern to greatly simplify our object creation and how we initialize our subsystems. We will then go to the structural patterns. We'll look at the callback pattern, which is a central pattern for implementing callbacks in a type-safe and very clear way. So we're not going to use any kind of generic pointers like void pointers. We're going to implement this in a type-safe way. And I'll show you how to implement callbacks that you can where you can register a callback that belongs to a particular object. So you don't just call a function, you have a specific context that also has to be accessed as part of the callback. And we're going to look at how to implement this in type-safe way. We're then going to look at the inheritance pattern, and C language doesn't provide built-in language primitives for inheritance, so we have to kind of think of inheritance as a conceptual concept. So we will look at some ways we can implement inheritance in the C programming language. We'll then look at the virtual API pattern, which is very central to any place where you need to treat different types of objects or different implementations in exactly the same way. So I'll show you how to implement virtual functions in C in a very memory efficient way and also type safe way, so we don't need to use void pointers anywhere. And then we'll look at the bridge pattern, which connects two different hierarchies of objects and allows us to seamlessly communicate between those hierarchies and keep our objects in sync. So that greatly simplifies the usage of or the interfacing with our objects. As part of behavioral patterns, I currently have only one section in this category, which is the return value pattern, where we look at the behavior of functions when they need to return some kind of status to the caller. And in our code, we want to check return values at all times. So this pattern is very important to set expectations about the return value, so that it becomes clear when you look at some code that checks for a return value, you know for sure that the value is going to be negative, for example, when there is an error, or the value will be 0 when there is no error, so, which means success. So we're gonna look at that pattern. And another pattern I would probably want to put in this category later is the memory ownership pattern, where we can actually have different types of pointers that have different meaning with regards to who actually owns the pointer. We might look into that a little bit later, but for now there's only one section in this one subsection in this section of patterns. And then we're going to look at concurrency patterns, and these are central for implementing any kind of concurrency. So if you're working with an RTOS, or even if you're working with just interrupts and you have some code that needs to interface with interrupts, then concurrency patterns give you clear ways of implementing concurrency safe code. So we're going to start with an overview of concurrency. We're going to look at how different priority levels relate to each other. So we can have interrupt priorities, and you know that interrupts can interrupt each other. So there is a little bit more complexity there. Then we're going to look at priorities of threads. And we're going to look at how we can interface between the interrupts and threads, and also how we can so we're going to start with a spin lock pattern that allows us to basically interface or implement concurrency safe code between multiple CPUs or between interrupts and other code. We're then going to look at the semaphore pattern that allows us to signal from an interrupt handler into a thread. We're then going to look at the mutex pattern, which is primarily concerned with threads and allows us to have mutual exclusion between multiple threads when they are accessing some kind of shared data. And finally, we're going to look at the conditional pattern, which is a conditional variable which allows us to signal from an interrupt and wake up multiple threads at the same time. Who is this training for? Well, most of all, this training is for software architects. So even if you've been coding embedded systems for many years, you'll find some ideas in this training which will clarify some things for you. And the main value of this training is to allow you to categorize different patterns and to understand when to use them and when to try to consider something else. So even if you are a very experienced engineer, you will still get some value out of this training. The second type of person you might be is a beginner embedded programmer. So if you're just starting out, then learning the right patterns from the start is the best thing you can do. And lastly, you might be an embedded manager. So maybe you're managing a team that is developing embedded systems. And in that case, it's very important for you that the team is following some kind of standardized set of patterns that keep your code base in good shape. That's it for this very short introduction to this course. I've shown you what is included in the course, so the next step is for you just to join, and I'll see you in the first module.